thanks for watching, and today is all about directional derivatives, which just answered the question, what is the derivative of u, not with respect to x or with respect to y, but in a diagonal direction. And this is extremely important when we solve first order PDEs. Now, in order to do this, we first need to define the concept of the gradient. So setting, suppose u is a function of x and y here. Then the gradient of u is simply the vector of all possible derivatives of u. So we write this as high-rule shield, or upside down u is ux and uy. So you collect the x derivative and the y derivative and put it in a vector. So just very concretely, if uxy is x squared minus y squared, then nabla u, a gradient of u, that is x squared minus y squared with respect to x, x squared minus y squared with respect to y, and that just becomes 2x and minus 2y. And it turns out this is enough to define the directional derivative, which we'll do next. So, definition, the directional derivative of u in the direction v and I'll post a slightly controversial definition, so is, namely, all you do, you take the gradient of u and you dot it with the vector v. And the reason it's controversial is a lot of books, they define v to have unit length. We will not take this definition in this case. So, but just as a remark, lots of sources, books require v to have length on. And the reason for this is, why am I not requiring this? Because in the end, in the next videos, we'll set this equal to 0, so it doesn't really matter what length v has. So here's just the simplest possible definition. So, for example, let's try to calculate the directional derivative of our function u of xy, which is x squared minus y squared, in the direction so in this case, I think I chose v to be 5/8. Is simply you take the gradient and you dot it with your vector. What's your vector? And you get, so we found this before, 2x minus 2y, you dot it with 5/8, and that becomes 5 times 2x, and then plus 8 times minus 2y, and that becomes 10x minus 16y. And last but not least, what does that even mean? So here's the interpretation. It's simply the rate of change of u in the direction v. And I'll illustrate this with a little picture. So in other words, what's happening here? So here's a little picture. Suppose, for instance, you have our function u. So not necessarily x squared minus y squared, but let's just have a general function u. So that's u of xy, and maybe we have a point xy here. So here you are at the point uxy, and you want to figure out what happens to the rate of change of u as you move in this direction v. So if you move in this diagonal direction, you may notice that this function curves up, and the answer is precisely the directional derivative of u, in the direction of v. So the rate of change is gradient of u dotted with v. And again, I know the scaling doesn't make sense, because if you multiply v by 2, that rate of change gets doubled. But as I said, we will eventually set this equal to 0. So in the end, it'll give us the same answer. And once again, this will be extremely important for solving first order PDEs, which is the next video on the playlist. Alright, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.